All right, now we're going to switch some gears halfway through the unit, and we're going into magnetism. So first part of this unit, the whole unit is called electricity and magnetism. We finished all the electrical material we had to, and now we're heading into our unit on magnetism. So the goal today, I can explain basic magnetic phenomena as it appears in the real world. So most of it's just going to be kind of talking our way through and introducing concepts and making sure everyone's on the same footing. So maybe rather than doing that, I'll bring this down a bit. So what are magnets? Naturally occurring magnets are known as lodestones. So there are naturally occurring magnets in the Earth's crust, and we call those lodestone. So magnetic fields. I've talked to you about fields before. If you remember, we have the Earth. It's the Earth, and you'd have your field strength, gravitational field strength. Okay, this is force at a distance. The Earth pulls you inward. The farther you are out, the weaker the gravitational pull. Then I talked about positive and negative charges. They also have field strength, electrical field strength. Okay, and the convention here is positive, pushes you away. Now we're heading into magnetic fields. Same idea. It's the same as electric fields, the same as gravitational fields. So we're looking at force at a distance again. So force of attraction or repulsion is caused by dipoles. So they don't have a positive and a negative. They have a north and a south pole. And those, because there's two poles, we call it dipoles. There's two defining characteristics. Magnetic fields occur naturally in substances that have magnetic character or internal that's looking at the internal makeup. Okay? And finally, they can affect not only other magnetic substances, but also electric charges, which is kind of interesting. So we're going to talk about how magnetic fields and electrical charge interact a little later on here. And that's why the unit is combined into those two particular concepts or topics. So let's talk about magnetic character. Magnetic character is related to the condition of the atoms in the material, and we still don't fully understand how this works. Okay, so that's why in this case we're talking about a theory. It's called domain theory. All right, and domain theory states that all large magnets are made up of magnetic regions called domains. And that magnetic character of domains comes from the presence of smaller units called dipoles. So dipoles are north and south, as I've mentioned already, and they interact with their neighboring dipole. If all of these poles align, then we get a larger magnetic domain. So what is domain theory? And you can describe it simply with a picture or a diagram. As I said before, a diagram is worth 1,000 words. So let's go with non-magnetic. So we're just going to, here's a microscopic or even closer view, and this is what we think is happening with magnets. So we have all of these little dipoles in here, and for non-magnetic material, they're kind of heading off in every direction. There's no real order or semblance. Okay, so draw those in, and it's in any particular direction. So we got a little bit of, call it chaos here. And go one that way, and finally one that way. So this is non-magnetic material. You have north, south, north, south, north, south, north, south, north and south, north and south, north and south, north and south. All right, and this is basically what it would look like, or this is the theory behind it. If it was then become magnetic, what happens then is all of those dipoles in there then align. Okay, so we get a very similar microscopic view. The difference is all of those dipoles now all line up. So now our theory is that this is what happens to all of those dipoles that we drew in there, that they all start aligning themselves as such, and that's what makes our material become magnetic. So everything matches up, and there's your domain theory. Okay? So domain theory, we believe that all material is made up of small dipoles, and when they all align, as they do in the second diagram here, we then have magnetic material. All right. So materials that allow for dipoles to be aligned to create a larger magnetic character are known as ferromagnetic materials. So not all material will do this, okay? It's only the materials that have some form of magnetic property. And those ferromagnetic, ferro means iron-based, okay? And some examples are nickel, iron, cobalt, etc., etc. So anything that we can create or make magnetic. So the law of magnetic force is similar magnetic poles repel. So it's very, very similar to charges. So similar magnetic poles repel. So that would mean a north-north. The resulting force would be a push, or south-south. All right. Your resulting force would be they would try to push each other away from themselves. Okay. And finally, dissimilar magnetic poles attract each other. So very similar to charges. So if we have a north and we have a south, they will be attracting to each other. Okay. So let's talk about magnetic phenomena. Magnetic induction. All ferromagnetic materials can be magnetized. All right. There is permanent and temporary magnetism. Some materials demagnetize easily. Others will hold on to their magnetic domains for longer periods of time. I'm sure most of you at some point, grade 2, 3, 4, magnetized a nail. You left it hooked up to a magnet overnight, and that nail became magnetized. That's a temporary magnet because those nails will not hold on for a long period of time. Reverse magnetization, a magnet can have its polarity reversed. So let's talk about, I'm going to give you a couple sketches here. So going back to the permanent and temporary magnets, if we have that material that is kind of jumbled up, all right, and I'm not going to bother drawing in the norths and souths. If we bring a magnet to it, so this is kind of stage one, let's say we bring in a material that is magnetized. So this is the whole magnet with nail, and you bring it into close proximity. All right. The result then will that original material will then become magnetized. All right. So if you put a nail on a magnet, it will become magnetized. Okay. Reverse magnetization. A magnet can have its polarity reversed. So that's saying that if I have a magnetic material, looks like this, and it is south-north, 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 and I bring it into proximity of a very, very large, powerful magnet that has its north and south reversed to the first one here. So I have my north and south, north and south. What will happen in stage 2 is that the weaker material will then flip its polarity. So that is your reverse magnetization. Okay, so the poles would switch ends, north-south, north-south, and you'd have reverse magnetization. All right. What else are we looking at? Breaking a larger magnet into smaller ones. What happens basically here is that if I have a large magnet, or a magnet, and it gets broken in the middle, so then my south broke like that. What happens is this would still maintain a south, this would still maintain a north, but now it becomes smaller magnets. So if a magnet becomes broken, it does not lose its magnetization, it simply becomes a smaller magnet. Now, maximum strength. I have here there's no limit to how strong a magnet can be. However, there are limiting factors. There is a limit to how strong a magnet can be. Naturally occurring magnets are kind of at your weaker end, and we can create stronger magnets with the use of electricity. And we'll talk about that a little later on in this unit. So sketching magnetic fields, and this is where it's a little bit different. The number of field lines are proportional to the strength of the field, so we've talked about that previously. And the direction of field lines is defined by the direction the north pole of the test magnet would point. So our magnetic theory is that our magnetic force lines go from north to south. So inside the magnet, we will have parallel lines in here. See if I can draw them properly. And I'm going to draw 4. So inside the magnet, we have evenly spaced or parallel lines. Okay, and it goes from north to south. So I'll put some arrowheads. When the magnet exits, or when the magnetic field exists outside the magnet as well, and what happens is you get kind of an elliptical field created, or they spread out like this in either direction. And you're going to see that in one of the demonstrations that you get to go through. And again, the field lines are going that way. So those field lines, again, when they are outside the actual physical magnet, we're going to call those the field lines. That's where that force at a distance comes into play, where it's repulsing or attracting materials. So you'll see that with the iron filings demonstration. And that pretty much summarizes or gets us through sort of the initial introduction to magnetism. All right. At this point, there's no homework associated with this one. This is just, again, getting everyone on equal ground, taking a look at and talking about field lines again. And we're going to move forward, talk about the interaction between electricity and magnetism in the next video.